Let's talk about quicksort algorithm. This is a divide and conquer algorithm that is recursive. This algorithm partitions the input a string array containing letters A through Z, and they're random. This is not A through Z in that order, but B, K, G, W, right, X. These are random. The first thing that we do is at each split, this is divide and conquer, we choose a splitting value right in the middle. Splitting value could be a value corresponding to letter K, corresponding to letter Z, W, X, Y, Z, doesn't matter, okay? In some textbook, this splitting value is also what we call pivot. The very first step is to group all of the elements that you have, letter R, L here, and this is group R, representing the right group. All of the elements on the left side should have a value smaller or equal to pivot or splitting value. All of the elements on the right side should have values greater than the splitting value or pivot. Or you can define it as such that the left side is less than pivot, the right side is greater than and equal to pivot. When you get into the recursive side, this is another split. There is going to be another splitting value or pivot, splitting value or pivot. This splitting value and pivot is different than the original. At each step along the way in each branch, you will need to find a splitting value to pivot partitions. This partition goes on until you have nothing to partitions anymore. If you look at this whole thing, quicksort, from a process standpoint, it looks very similar to a heap, right? Where all of the values sitting on the left side is smaller than the root. The values sitting inside each of these buckets, they're not necessarily sorted. They're just smaller than we know. And that's the whole point, right? Having this quicksort to be able to quickly sort them out by divide and conquer. The order is being established, right, from top to bottom. We are not creating additional arrays here. This is all of the same array. What is being divided here is a invisible boundary, which uses the index to specify the location of the split or the partition boundary. There's movement of these pointers moving around from left to right, right to left. Eventually, you see a swap. All of this is swapping in place, meaning there is no additional cost. There's no additional memory required. Quicksort is very efficient memory-wise because it uses it in place, and especially when you're using an array, O of one access, doing a swap is a constant, right? This is extremely fast and log n time complexity for quicksort. Let's just look at how a recursive call like quicksort could be established. The recursion starts here. You have to have both the base case and general case, a way to generalize the whole thing. So the way that you would generalize the entire algorithm is to split them into three parts. One is the split part. This is what we call the partition. This partition is the bulk of all of the logic that we need to describe. That's general case. The base case is if the size is less than 2, do nothing. Why? Well, if you have only one element, there's nothing to sort. So the divide and conquer basically ends at size equals 1. Or even sometimes size equals 0. So if size is 0, that means there's nothing in there. In that case, what is the size? Size is less minus first plus 1. If you have some input and that has your first being here, and then your last being last of the element. So the total number of elements that you have in there is last minus first plus 1. This is a general formula for computing the number of elements you have in there. So once that size goes down to 1, less than 2 in general, you just return it. So this quickly wraps up quicksort. The bulk of the logic sits right in here in a split array. In the next video clip, we're going to talk about the split partition logic to complete the discussion on quicksort.